Hello everybody and welcome. Today we are solving a thermodynamics problem in which we are solving for the pressure needed to lift a piston from static equilibrium. So first, to start solving this problem, we must start with what we know. So the problem gives us that the atmospheric pressure is 1 bar. And first of all, before I start, it is a piston cylinder under a heat plate or over a heat plate. So the heat, it's providing constant heat leading for pressure to expand. And the main thing here is that the piston right now is being forced down on the stops by the atmospheric pressure and its own weight, which is just mass times gravity. So we need to solve for when gas is equal to the forces of the atmospheric pressure and the weight of the piston added together, because at that point, that is when gas pushes, and that's when our piston begins to rise. Because at that point, pressure will want to expand more, expand more. But since it is a piston, pressure will stay constant, and actually volume will begin to expand. So we only need to find when the gas is equal to the force of the piston plus the atmospheric pressure. And as I said, here are the stops. This is our gas, not given a specific gas, and our heat. And right away, just write out the force balancing equation we will use. So our force of gas is equal to the force of the piston plus force of atmospheric pressure. Now, our first step in this specific problem is we want to first solve either the piston or the atmospheric pressure. Either one doesn't matter. Let's just go with the piston. So, what do we have from the piston? We have the kilograms and the area. And in this point, I also forgot to add, we have gravity, 9.81 meters per second squared. I should probably write it a little bit bigger, but. So, in this case, it is either W for weight or force for piston. Either one doesn't matter, but since I said weight, we could do weight. But force is the same as weight, essentially, in this problem. Okay. We know that the weight is equal to its mass times its gravity. So, using this, we have 50 kilograms times 9.81 meters per second squared as our weight. Now, the trick with a lot of thermodynamics, or what gets people especially, is just knowing your unit conversions. It could be a lot, and it gets a lot once you go into, or you start using English units as well as SI. It's a lot to keep track of, but just takes practice. So by looking at this, I see kilograms times your meters, and that's over seconds squared. And I notice that that just converts to newtons, which is exactly what force or weight is. So from here, we multiply 50 times 9.81. Sorry about that. And we get a force of 490.5 newtons. 490.5 newtons. Could add the F. The force or weight of the piston, however you want to keep them labeled. So now we will solve for the force of the atmospheric pressure. So pressure is essentially just force over an area, which is the exact equation you will be using right now. You want to manipulate this so that you get your force is equal to pressure times area, your two knowns to solve for your unknown. Now, we are given that the pressure, atmospheric pressure, is 1 bar. So from here, 1 bar, and since in this problem there is nothing like, I guess, no, how should I say it? No external work like a shaft in another problem that I've done. No shaft or anything blocking the entirety of its area. So essentially, it's just a cylinder, and you don't have to subtract any area that it's from, like I said, a shaft or any external forces. So our 1 bar, and it's actually nice because we are given area when usually we could be given diameter or radius. And in this case, or in that cases, we would have to solve for area manually, which is just pi r squared, or 1/4 pi times d squared. But we don't need that right now. Right now, we have the area. And so we multiply our pressure and our area of 0.01 meters or meters squared. Now, you can't just multiply your bar and your meters squared, because that's not a unit. So what we need to do is turn 1 bar into Pascal. And the reason for that is because Pascal is actually Newton over meter squared. So we know that 1 bar is equal to 10 to the 5 Pascal. And Pascal's units are Newton over meter squared, which would perfectly cancel this meter squared to give us our Newton of force, which is perfect. So we must translate or convert, 1 bar to Pascal. And so we want 10 to the 5 Pascal up here, and bar in the denominator to cancel what we currently have. So our bars cancel, and at that point, it's just 10 to the 5 times 1 Pascal. 10 to the 5, which is just 100,000. So we have Pascal, Pascal, which is just converted to 100,000 Newton meter squared. Sorry if any of my words confused you prior, but so this is our pressure. We successfully converted it to Pascal, and Pascal is just Newton meter squared. Newton over meter squared. So now, simply just looking at our units, just to prove that they cancel, and we end up with Newton. So from there, we need to multiply 100,000 times 0.01. Times 0.01, which is just 1,000 newtons. And that force is from our atmospheric pressure. So now, what do we do with these two pressures, or these two forces? Now, we are able to add them up to solve for the force of gas needed to lift the piston from static equilibrium. So our F gas is equal to the force or weight of the piston plus our force of atmospheric pressure. So from there, we do 490.5 newtons plus 1,000 newtons. This work is all over the place, so I will improve as time goes on. Keeping it neat. So now, with our 1,000 newtons, we want to add the force of our piston, 490.5 newtons. And that gives us our gas force, which is equal to 1,490.5 newtons. Great. So this was essentially our step 1, step 2, step 3. Now we have done a lot of work and we did get our force for gas, but remember the problem asked for the pressure in bar needed to lift. So going back to our pressure equation, we will use our force of gas and actually divide area from it. So let's label this 4 because we are solving for the pressure in bar needed to lift the piston from static equilibrium. We will use the force of the gas, which is 1,490.5 Newton, over the area, which is 0.01 meters squared. And the area is that of the piston. And the piston is just a circle, essentially, its area. So, yeah. Well, we didn't need to calculate it, so it worked out for us. But anyways, here is our pressure. The force over our area of the piston's face, which is just a perfect circle. So, now doing the calculations, we get 1,490.5 divided by 0.01 meters squared. And now, don't forget about your units. You have newtons over meters squared. And what did we transform into Newton over meter squared previously? Our Pascal. And so, that is how we will get back to bar. Or, yes, exactly. That's how we will get our bar for our pressure force, which is what the problem is asking. So that just turns into Pascal. And so now we have our pressure is equal to 149,050 Pascal. Perfect. And now we will need to translate back into bar. And so in order to get Pascal back into bar, running out of room, so I'll just show the units. Pascal, and then the conversion ratio for every 1 bar, it's 10 to the 5 Pascal. So you need to divide this pressure by 10 to the 5. And your Pascal units cancel out, leaving you with 1 bar, or 1 bar, and that's just multiplied times that after you divide. divided by 10 to the 5. Perfect. So now you have your final pressure needed to lift the piston from static equilibrium is 1.4905 bar. But we could round that up to 1.5 bar. Perfect. And now you have solved how to find the pressure needed to lift the piston from static equilibrium.